Recording. Okay, good. So that's the longest phenomenon, and then now we are going to use the Chebyshev node device and Chebyshev interpolations to create these quadratures, and then it is called Crenshaw-Curtis quadratures. And you will see the Chebyshev node device is defined in this way, and we have more points on the boundary instead of the equally distributed. So now let's see. We have several things. We have the Chebyshev node device, and this is one important thing here. Chebyshev node device, and then with this Chebyshev node device, and then we have the Chebyshev interpolations. And so let's see. So first we are going to get the interpolation of the function, and then we would do the integration of that interpolations polynomial, and that is our Crenshaw-Curtis quadratures. So let's see what we have is the Chebyshev interpolation. Chebyshev's interpolation, and if you remember what we have learned from the Chebyshev interpolation, and then we have, so assume we are working on the interval -1 and 1, and then that interpolation, it should look like this. This is our interval. So what we are going to do is to approximate. So let's say the goal is to, so today's class is to, first, we are going to get one simple example, and then we are going to approximate the integral. And then that is the -1 to 1 and the fx dx. That is the integration on this simple interval. And later on, we would generalize this integrations to a more general case. And so first, let's record what we have in the Chebyshev interpolation. And Chebyshev interpolations of function f at the Chebyshev node point. So Chebyshev node point is expressed as above. We just mentioned how to deploy decide the Chebyshev node points by the cosine function, and we have the interpolations. It looks like this. So p and x. So for any x, so here is for any x, and then that's x is belonging to the -1 and 1, and then the p and x. This function can be, this is the Chebyshev interpolation, is something similar to the Lagrange interpolation. It's just the interpolation of the polynomial of the function. We have such a format, and then I will tell you the value of the AK in a minute. And I will also tell you how to define the basis function here. So now, similar to the Lagrange polynomial, and then we have the basis function, we have the coefficient here, and then what is the coefficients? And with the coefficients, given by, and we have the AK equals to 2 over n, and my sigma sum n j equals to 0. And then this one is the function f evaluate at the theta j, cosine theta j, and then cosine times the cosine k theta j. And at this moment, you don't know the theta j definitions, but here, the theta j is actually, theta j is just the j pi over n. And then the j could be, the k here, it could be like from 0 and then 1 and then to the n. And this is because like we already have the Chebyshev Snowden voice, and then it's just like cosine j pi over n. So corresponding this theta j here, this is the theta j, and then corresponding to this theta j, and then we have evaluate at this point, and then evaluate at this is the xj value. Do you see? This is the xj. It's actually the xj. And this one is just a cosine k theta j. And this is how we calculate the things. And this is actually the fxj. It equals to it is just the fxj. That is the function evaluate at the loader voice, but here we have the cosine k theta j for another things to multiply. And this is the some things we have already learned in the Math 104A. And today we are going to use this Chebyshev interpolation to get the Cranshaw's quadratures, which means that we are going to integrate this function here. Wait a minute, and I haven't defined the basis function yet. So we just define what we have in this interpolation, that is the coefficient, and we still have one things to write down, and then that should be the basis functions definitions here. For the Chebyshev interpolation, and then the T and X. Let me see, the T and X is defined with, it's just a cosine and theta. Cosine and theta. And then where the theta X is cosine theta, and then theta is between this one. The theta value is between the 0 and pi because the x value is in between -1 and 1. Does it make sense? Because on this interval, this cosine function is so let me just draw the picture here. The cosine function. This is the cosine function. This is 0 to pi, and this is the cosine functions on the interval, and 0 to pi. And on this interval, you will see this cosine function is vary from 1 to -1. Does that make sense? So, which means that this cosine theta function is actually mapping this interval 0 to pi, and to the interval, and then to the interval -1 and 1. So, which means that the cosine function is mapping this 0 to pi, and then to the -1 and 1 interval. And this is the interval transformation here. So, which also means that, so for each x value from the -1, and then you can find out the corresponding theta value to represent the x. So here the t and x is just defined by the corresponding theta here, and then it's cosine and theta. And this is the old definition, and it looks very complicated, but let's do the calculation. And the calculation here we have. So let's copy down what we have in this function. This is the interpolation of the f, and I just I have told you the general idea of the quadratures, the interpolatory quadratures. We get the interpolation of the function and then integrate that interpolation, and then we get the approximation. So Pnx is the approximations of the f function. Now let us integrate the Pnx, that is the interpolations on the interval a and b. Because here we just work on the simple case, and then that is just -1 and 1, which means that we are going to do this integrations, and it's just the Pnx dx. Let me see, am I right here? Yes, should be correct. And we are going to use this to approximate the -1 fx dx. Okay, good. So now the things we come to do this integration, and I have just saying that, okay, what is the transformation here? The transformation, so now I'm going to use that formula I just write down, and Tnx, right? Here is represented by the Tnx and then Tkx, and then I'm going to just change the variable here, and then change the variable to theta. And I just use this x equals to cosine theta here to change each variable x into theta in terms of theta. So this is a variable change here. Let us do variable change. Let us change the variable by letting x equals to the cosine theta. So if we do the change of variable here, what can we have is -1, 1, and Pn. Okay, x is just a cosine theta, right? Cosine theta. Good. It's just a cosine theta. And what about the dx? Do you remember something? This is something learned by the in the calculus class. Because the x equals to the cosine theta, and then the dx should be equals to, what is the d theta? Dx equals to something, and then d theta. And then this things here, it should be the cosine theta derivative. Does that make sense? Do you remember this? In the calculus class, this is the change of the variable. This one, the cosine theta, we have the derivative. Let me see. It should be negative sine theta, right? Does it make sense? So if I change the variable here, it should be negative sine theta d theta. And there's one thing I need to change here. And then I should not write this down so quick. This one, -1 and 1. Because I have already changed the value. So I have used this cosine theta to change the theta range to the x range, right? And let's see the correspondence here, okay? And so for this mapping, and when x equals to 0, and then it is corresponding to pi equals to when x equals to 1, and then it corresponding to pi, the theta equals to 1. So this one is the theta axis. And this is the x-axis, x value. So when x equals to 1, which means that x equals to 1 right here, and then it's corresponding to the theta equals to 0. And when x equals to -1, and then this is the x This is the x-axis, x equals to -1, and we have the theta is corresponding to pi, right? So now I'm going to change the value here. The integrations limit here. The 1 should be corresponding to 0. This is the change of the variables, and then we need to change the integrations limit as well. The -1 is corresponding to pi. And because I have a negative sign here, and then I have this integrations limit here, I can flip the integrations limit upside down, and then by combining this negative sign. Does it make sense? Okay. So this equals to the 0 to pi, and then Pn cosine theta, and then sine theta d theta. And we are going to do this integration to get the whole things we have here. And so now let's see. Here it should be like Tnx and then Tk, and then for any k, it's between the 0 to n. We just have 1, so we have 1 to n. Okay, good. So let's get back to here the integration. And what do we have here? The Pn theta, the Pn theta, sine theta. The Pn cosine theta, I'm going to move this down. I have Tnx. So I'm going to have 0 to pi, and then going to have the Pnx here, and then the Pnx looks like this. And then what is the Tkx? The Tkx equals to the cosine k theta. Is from the definitions above here at the top. Is equals to the cosine k theta. So I'm going to replace these things with cosine k theta. This is the cosine k theta. And Tnx is just the cosine and theta. And theta. Good. So what do I have? Rest. I have the sine theta here from the change of variable. And then this is the d theta. Can you see this happening? This is the Pn cosine theta, and then I just change the variable. And originally this is the Tkx, but the Tkx is equals to the cosine k theta. And this is originally, this one is the Tnx, but I changed the variable, and then I got the cosine n theta. And this one is just from here, the sine theta here. I'll just copy that. And this is the calculation. And if you don't understand the whole thing, it doesn't matter, because this is the most complicated quadrature rule you need to learn from this class. And maybe you just need to know, oh, there's something there. You can get faster convergence than the Simpson rule. Faster convergence and more accurate, maybe more accurate than the Simpson's rule. If you do the same node voice, the number of node voice. So now we are going to do this integration, the whole things. So for the first item, we have the A002, and then it's just the integrations, 0 to pi sine theta d theta. And then for the rest, we have sigma sum k equals to 1 and -1, and then I just extract the this one, the coefficients out, and then I got cosine k theta inside, and then sine theta here, and then d theta. And then the last item I have is AN/2, and then is the integration cosine and theta, and then sine theta, d theta. And this is quite a long trigonometric polynomial integration. And the things I'm going to have. So for the first item, what's the antiderivative of this one? It should be like negative cosine theta, right? And then evaluate at 0 and 1, pi, 0 and pi. And then it's just the A0 over 2. And if we evaluate at the 0 and pi, and then we get this, it should be the -1, and then -1, then minus the -1. Is it right? Am I right here? So cosine pi here is just like -1, but I have a negative sign here, and then subtract, evaluate at 0 here, and then it should be 1 here for this one, and then so I have a negative sign here as well. So at the end of the day, this is just 1, and then this is +1, and then divided by 2, and then I got 0, A0. Does make sense? Okay. The first item, the first integration, I got this whole things. This whole things. It equals to A0. And the next, I'm going to do the integration for cosine k theta, sine theta. And we need to use one thing here. And this is from the calculus class. Cosine k theta and then sine theta. And this is another trigonometric identity here. It's equals to the sine 1 plus k theta, and then plus the sine 1 minus k theta. And this one, it looks nicer if we want to do the integration. And then we are going to do the integration of this part, right? And then let's do the integration. And then that is the same one as this one. And we have the different, this one is just the n. And so now what is the integration? See yourself here, we have the cosine k theta and then sine theta d theta. And then it equals to the 0, pi, and then we just use the identity, trigonometric identity upside, above, and then we have this one. And this one is easier to calculate because this is a sine function. There's no product here. There's no sine, and then times the cosine function, and then it's easy to get the antiderivative, right? And so now, could you tell me what is the antiderivative for the first one? By using their chain rule. There's some chain rule here. So it should be like negative cosine 1 plus k theta. And then is there anything else we need to put it here? If you take the derivative of this function, just right, and then it should be like sine 1 plus k theta. And then you need to take the derivative of the 1 plus k theta as well. So you have another 1 plus k theta, 1 plus k. So here it should be 1 plus k. So that's the same thing here, negative sine 1 minus k theta, and then 1 minus k. And then you evaluate at the 0 and pi. And there's a 1.5 here. Now I'm going to let you do something. Let's do this. There are 2 cases. So case 1, the k is even number. And then, so if the k is even number, and then what is a negative cosine? So I'm going to evaluate all these things here. Evaluate these things at the pi. And then it should be, I write this wrong thing here. It should be a cosine. And then negative cosine minus 1 cosine k theta, it should be pi. And then 1 minus k. and then equals to 1/2 here. There's a 1/2 coefficients, never forget this one. And then another thing is to evaluate as 0, and then it should be like negative cosine 0, and then 1 plus k, and then minus cosine 0, another cosine 0 here, 1 minus k. Okay, that's the things. So the last two is just like cosine 0, and then it's just like equals to 1, right? Equals to 1. And the problem is that what is the cosine 1 plus k and then pi? And because this is a even number, and then even number plus 1 is an odd number, or 1 minus k is an odd number, right? So let's do this. Let's go to the circle, and then to get the number of the cosine value. And we have already learned this in the algebra class or the calculus class. We can get the cosine value from the unit circle, right? So now we have odd numbers of pi, which means that, okay, here is just the begin here is 0, and then this one is 1 pi, and then 2 pi, 3 pi here. This is the odd number pi, and then what is the cosine value here? -1, right? Okay, so we get -1, and then -1, and -1. And we get -1 and -1 here. And then this is 1 plus k, and this is 1 minus k. This is 1 plus k, and then minus 1 minus k. Am I right here? Do I did anything wrong here? No. Hopefully no. There's a -1 here as well. Okay. Okay, good. So at the end of the day, I got 1 plus k here, and then there is another plus 2, and then 1 minus k here. Am I right? My question is, am I right? This is the this should be this addition sign, right? This should be the addition sign. This should be the addition sign. This should be the addition sign. So it should be at the end. I got this. This should be the subtraction. I got 1 over 2, and then times 2, and then 1 plus k minus 1 minus k. And at the end, I got that is just the 1 plus k, 1 minus k, and then 1 minus k minus 1 plus k. There's something wrong in my calculation, I guess. I'm not sure where I get wrong here in the calculation. There should be something wrong in the calculation. Let me see. At the end, at the denominator, I got 1 minus k squared. And at the top, originally I should get this should be the, I think there's something wrong here. Let me see. Yes, it should be. Yes, it should be the negative sign. I get it wrong. Yeah, I changed the negative sign to here. It should be the negative sign, the minus sign. Sorry, I changed it to the wrong things. It should be the minus sign. Minus sign, and then so here at the end, this is additions. This is a summations, and this is the summation, and this is the summation. And then, so now we can cancel the minus k and then k plus k. And then we just get 2 here. And at the end, this is all the calculation, the integration, which means that the integrations of this one. So I'm going to give you the conclusions. So when k is E1, and then the integrations of the cosine k theta sine theta d theta, and then it equals to the 1 over 1 minus k squared. And the second case is that, so case 2 is the k is odd number. And everything is the same here for the odd number, and then it's the same, and then the thing that is different is this number, and then this one become to this one. Let's take a look at here. If this one is if this one is the odd number, and then what can we get? If this one is odd number, and then this is the E11, the E11, and then you would get this one. It's just go to the 1. It's not the -1. So here we would get, so I'm going to copy down all these things here, and it would just change the sign here, just change it one side, because if the k is odd, and then this one we have, if the k is odd number, and then 1 plus k is just the E1 number, and then we have E1 number of pi, and then let's go to the circle again, and this is odd number, E1 number, odd number, E1 number. So 0, 1, 2, 3, and 4 pi, and then the cosine function at this point is just 1. So I'm going to change the value here because the k here is just equals to 1. The cosine function is just equals to 1. So I got 1 here, and immediately you would say this one is -1 over 1 plus k, and this one minus and negative. So it means that we plus 1 over 1 plus k here, right? It just get canceled, and then the same things happen to this one. The 1 over 1 minus over k, 1 minus k, and then we get these things get canceled by these things here. This is the subtraction side here. Let me write that down. So at the end, we have the odd number 10 is just disappear. It's just disappear. And so we can conclude that. So let's copy down what we have at the very beginning. We just have from here, right? We calculate the, we have calculated this part, and then it just remain the E1 order 10, E1 index 10. So at the end, we get, okay, I'm going to erase this part. And the first item is just equals to A0. And then the second item from the calculations below, I got, so for the index 10, and then it just disappear. So from the E1 order 10, and then it's the k equals to 2, and then to the n minus 2. So I'm also want to say that the n here, the n node voice here, the n it should be the E1 number. And I have, what do I have here? I have the k, and then k is E1 number, and this, the integration I got here, it should be like 2, and then divided by 1k squared, 1 minus k squared. This is the things I have here in the E1 cases. 2 over 1 minus k squared. This is the results I get from the integration. And then I also have the AK coefficient here. And then I have a an over 2 here. And because the n is the even order term, so I also have some value here. And then the n here, it should be like an and then 1 over n squared. And this is the Crenshaw's quadrature rule. And that's it. This one should be like 2. And this is the result from the integration. So I'm going to do some conclusion here. And then it's just that k equals to 2. K is the even number 10, n minus 2. And then 2ak, and then 1 minus k squared. And then it's equals to an over 1n squared. And this is the things we call Crenshaw's Curtis Crenshaw-Curtis quadratures. And the definition of the A0, AK, AN, we just mentioned above, and then I want to point it out again. So let's see, I'm going to write down, conclude all these things here. So this is the Crenshaw-Curtis quadratures, and it's used to approximate the integrations on -1 and 1 fx dx, and then equals to, and so here we are going to approximate it with the formula below, and then it's just equals to the k equals to 2, and the k is E1 again, is k is even number. And then for the 2ak, and then 1 minus k squared, and then plus the an, and then 1 minus n squared. And the an definitions, I just want to copy everything down. And then the ak, the ak here is defined with the Chebyshev interpolation, and then the ak is just defined by this number. It's a 2n and then second sum of the f cosine theta j cosine k theta j, and then this is the number we have here for the ak. And AK is easy to calculate with the fast Fourier transform, and then this should be mentioned in the method 104A. And if this is not mentioned, and then it doesn't matter. This is just another, you can treat it as a constant, just some constant. And then there's some summation here. And this is some advanced things you need to know. So it's not quite required in your exam part or your homework part. I'm not going to give you some difficult questions on this part because it's quite complicated. And is there any questions by so far?
Did you forget to multiply an over 1 minus the square root by 2?
Which one?
If you scroll up.
Uh-huh.
Yeah, more where it's highlighted. Plus an over 1 minus the square. What we divide.
Oh yeah, we divided that. Mm-hmm. Questions?
You have to do that whole process like differently. Instead of -1 to 1, it was like 0 to 1, which got that example like 0
Yeah, I expect that question. So I expect this good question. I am waiting for this question actually. So -1 and 1 is quite restricted, right? You have a lot of interval. You have different places you want to do the integration, and then now that's another thing is change of the variable. This is the game of the calculus, and now you can. So for example, you have a general. Yes, thank you. This question is I'm waiting for it. And this is a general case. A general case, you are doing the integrations on A and B. And this is the integrals you want to approximate. And if we want to approximate this integral, and then we can do this. We are going to do some change of variable here. And change of variable, which means that we are going to change the variable a to b to the variable -1 and 1. That is what we have mentioned just now. We have the formula for the interval -1, 1, and 1, and we want to change the interval a to b to -1 and 1, and that's what we want. What's the change of variables formula? The change of variable formula is x. Actually, we are working on the integration there, and then it should be the let me see, it should be the interval 0 to pi. And so you can change the variable x to some middle value, and then it's in the interval -1 and 1. But at the end, you can change it to theta, and then that is 0 to pi, right? And which means that, so let's take a look at this change of variable here. And b minus a, and then 2 cosine theta. So for this change of variable, it's going to change the value. So there's a mapping here, and then it maps the theta, and then that is from 0 to pi. And then it maps to the x, and then the x is in the interval a and b. So let's see. If you substitute the 0 into this things, and then it's just the cosine 0, and then it's just 1. So this is just the b minus a divided by 2, and then we do the addition here, and then it gives you the b value. Does it make sense? If you substitute the pi here, and then you would get the a value here. So now you have the change of variable, change the theta to the x, and then there's a correspondence here, right? So now with this change of variables formula, this green part, and then we are going to change this integrations into, and this is becomes to, I'm going to do the substitution here, the fx, and then I'm going to substitute the x with x plus b, and then divided by 2, and then plus b minus a, and then divided by 2 cosine theta. And I'm going to define this function as an Ardèche function, and then this is the function of zeta. Just substitute the x with that formula. And then now I get this one should be the integration on the interval, and it's about the theta, f theta. And then what about the dx? Dx again, so for the variable transformation here, the dx, and then we got it equals to the derivative of the x about the theta. So I got, it should be the sine theta, d theta. I also changed the sign here, the 0 and pi, it should be. So I just split originally this one, the a corresponding to pi, and then b corresponding to 0. And then the derivative of this one, it should be negative sine theta. But I combine the negative sign and then flip the integrations limit here. And this is how I change this one to this one. And then now for the f theta again, you are going to use the p and theta here to approximate it. That Chebyshev's polynomial. And then use the formula there, and then that's it. So this is how we do the general case. And this part you can use the p and theta, yeah. And then once again, you are going to use that p and theta, and then sine theta, this theta, and then you are going to use that integrations, use this formula we got here, and then to approximate that integrals.
When you take dx, what about B minus A over two, whatever it was.
So dx is the,
Yeah,
yeah,
B minus A over two.
b minus a over 2. Yes, you are right. You're right. I missed something here. It should be b minus a over 2 and then negative sine theta. Thank you. And b minus a over 2. Thank you. And I have already get everything that you need to know. And so on the lecture notes, I have another lecture notes not here, but you can go back to take a look at the lecture notes. I have give you one concrete examples on that one, and then it tells you the benefit of that quadrature's Cramshaw's things. Let me see. Do I have the canvas here? So wait me for like 1 minute before your holiday. Here. Quick. So if you go to take a look at your lecture notes here, and then there's Crenshaw things here. And I'm going to show you real quick where here. Is this mine? So let's see. This is not mine. So I'm going to let you go, and then we would go back to, oh yeah, that's the one. Okay, good. So this is the pictures. And this one, the blue one is the Crenshaw-Curtis one. And then this one is the composite Simpson-Sue. And this one, the access here is the error. And then this horizontal one is the node voice we use. And as you can see on these pictures, we just use a node voice to achieve something similar to the error is close to the machine precisions. The machine precision, it should be like 10 to the negative 16 in the double precision setting. But here, if you use the composite Simpson rule, how many points do you need to approximate to the error close to the machine precision? It's over 500 points. And that's the benefit of the Crenshaws. You just need like 8 points, 8 node voice. You don't need 500 node voice. So faster convergence means that you can do the calculations faster. And that's all. See you next weekend. That's the weekend. Go. But there's homework.